In this section, let's take a look at solving by substitution. As you can imagine, looking for a solution by first trying to figure out what type of equation you have runs into the problem that some equations just don't fit any of the nice categories that we've already seen. Now, of course, there are other techniques that are going to be used for other types of problems. However, we can still use some of these techniques that we've seen so far, like looking at linear equations, looking at separable equations, by considering substitutions. Okay? So, let's begin with a definition here. Let's say you have a function of two variables, x and y. Then we say that the function f is, and there's two ways of pronouncing this. Some people say homogeneous. Personally, I've always said homogeneous. It really doesn't matter. It's just a difference in pronunciation. F is homogeneous of degree alpha. If the function has a property that if you multiply everything times some value, which we'll call t, multiply all the variables x and y by t, then that's the same as taking that same t to some power, which that alpha is this alpha here, times the function as it originally stood in terms of x and y for some alpha. For some real number alpha. So for example, let's say I have the function f of x comma y is equal to x squared minus xy. Okay. To test to see if this is a homogeneous function, we're simply going to replace x with x times t and y with y times t. And let's see what happens. So if I say all the x's get replaced by tx, that x becomes tx quantity squared. That x becomes tx. This y, if I replace it with ty, that means I'm replacing this y with ty. And now let's simplify things out. If I square this, I get t squared x squared minus t times t, that's t squared xy. And I have a common factor of t squared, which I will now factor out, giving me t squared times x squared minus xy. But if you notice, this right here is the original function that you started with. So you can write this as t squared times f of xy. And so the function that you started with is such that if you replace the x with a tx and the y with a ty, then you can simplify out to get t squared times the original function. So this does satisfy this definition with alpha, the power being 2. So here this original function, so f of xy is homogeneous of degree 2. Okay. All right, so with that definition out of the way, let's consider another definition. Let's say you have a first order differential equation. A first order differential equation in differential form. If you don't remember what that is, that's the one that looks like this, mxy times dx plus nxy dy equals 0. This type of equation is said to be a homogeneous differential equation. We say homogeneous differential equation if both the function m and the function n are homogeneous of the same degree. So it's not sufficient that they both be homogeneous, they would both have to have the same degree as well. Degree 2, degree 2, degree 3, or whatever. If both m and n are homogeneous of the same degree. All right, now note, if you have such an equation, in fact, let's write this as a note. Note, given a homogeneous differential equation, we can write well, let's see. My function m of xy. We know we can do something to the function, or rather we can do something to the variables of the function, and as long as it's the same thing that you're doing to both, that thing can be brought out with some power, whatever that power might be. All right? Okay, well, what are we going to do? Are we going to just multiply by t the way we did up here? Well, we could, but we're going to be a little more specific.
Okay, first.
All right, so let's multiply by, I guess we'll start with, let's do 1 over x. So here, I'm going to multiply both the x and the y by something, but the something I'm going to choose is not just an arbitrary t, it's going to be 1 over x. The same as that x right there. Okay, well, if I do that, I can write this as this common term, 1 over x, this common factor, can be brought out with some appropriate power. We don't know what it is, but we know it's something we call alpha. So it'll be 1 over x to the power alpha times the original m of xy. I should not have written an equal sign here. These are equal, but these are not. So here that's, I'll just put a little colon here. So speaking of this one, this equals this, yeah. Some bad notation on my part there. Okay, so that's going to be 1 over x m of x comma y. All right, so if we then let, so here x over x is just 1. Y over x, on the other hand, let's go ahead and simplify that. So let y over x be written by, we'll use the symbol u. You can use whatever symbol you like, but use a pretty common substitution. This then becomes that m of 1 comma u, like this, is equal to 1 over, 1 to the power alpha stays just 1. So I think I'll just put the alpha on the denominator. That's x to the power alpha like this, times m of xy. Okay? Here we can go ahead and take this and multiply to the other side. We get that the m of xy that I was considering at the very beginning is in fact equal to x to the power alpha times m of 1 comma u. X to the power alpha of m times m of 1 comma u, like this. And similarly, you could do the same thing with n of x comma y. Considering that one, we could say, well, because n is also homogeneous of the same degree, it'll follow the same result. So here you would have n of something times x, comma, that same something times y. That can be written as 1 over x to the power alpha, that common factor to the power alpha, times n of x comma y. And again, that's just the property that we get because these are both homogeneous. But then using the same substitution here, y over x is equal to u, we get that n of 1 comma u is equal to 1 over x to the power alpha times n of x comma y. And same as before, bringing this to the other side, we get that this n of x comma y that we began considering is in fact equal to x to the power alpha times n of 1 comma u, where u is equal to y over x. Likewise, if we say u is equal to y over x, we get, well, this is equal to this, and this is equal to this. Likewise, if you switch that substitution, if instead of y over x you do x over y, Let's not use U, let's use V this time, just a different letter. Likewise, if you take x over y to equal to v as your substitution, counterpart to this one here, you get, and you can try this yourself to see if you can develop that, but it's the same development as this, just with this substitution instead of this one. You end up getting that m of x comma y is equal to y to the power alpha times m of v comma 1, and you end up getting that n of x comma y is equal to y to the power alpha of n of v comma 1. So here, it looks like these substitutions will simplify our expressions down to something smaller of a single variable u. This suggests that we now have a technique and a substitution to get that technique started. So, technique. And this technique is for solving a homogeneous differential equation. Doesn't matter what order it is, as long as it's homogeneous of some order. Something that looks like p dx plus q dy equals 0. Okay. So first of all, what you want to do is you want to confirm that it's homogeneous, because if it's not, obviously this technique doesn't work. That's usually the first step of any of these techniques, isn't it? Confirm that the technique is valid. Confirm that this is the technique you should be using. Confirm that the equation is homogeneous by just checking that p and q are both homogeneous of the same degree, of degree alpha. Next, we're going to use our substitution, and the substitution can be either of the two that we just saw, and here we'll restate them. Substitute. I have to learn how to spell one day. We'll substitute either y is equal to u times x, or the other one we can do is we can do x is equal to v times y. These are our substitutions from before. Here, if you let u equal to y over x, you can multiply the x to the other side, isolating y equals ux, which is the first one. Or for this one, you can multiply the y to the other side, getting you x equals vy. X equals vy. Either of those is fine. When you make that substitution, you will change not just the variables x's and y's, but also the differentials of x's and y's. So here, well, let's see, if I wanted to substitute y with something, that's going to affect all the y's in my problem and the differentials of y in my problem. But we know how to find a differential. A differential is just, well, you take the derivative of this thing times the differential of the variable. Right? So in differential form, what that is just the product rule. It's going to be the first one times the derivative of the second. This is u. Now, this should be x prime dx. That should be x prime dy, but really that's just dx. The derivative of something times the differential of its variable is just its differential. So right now we're just using the product rule in differential form. So that's going to be the first times the differential of the second, plus, and then we take the second one times the differential of the first. Like that. And same thing here. If you remember these together, then all the substitution just gets plugged in. If you just want to remember this one, you can always derive this one, because again, it's just the product rule in differential form. Here, dx is equal to, again, just the product rule. That'll be v dy plus y dv. When you do that substitution will then change your homogeneous problem into a different kind of problem. Maybe linear, maybe separable, maybe exact, or maybe some other one that we haven't seen yet. But the last step is to now, after you've substituted in these expressions, or these, whichever you prefer, we're going to simplify and reclassify. And again, so far really our only options have been linear, separable, What else have we had? We've had exact and, other. There are others that we haven't seen yet. You're going to simplify this, reclassify it into some other type of problem, and then solve that new problem. So for example, let's go ahead and consider the problem xy minus y squared dx plus a negative x squared, and I could say minus x squared, but plus a negative, same thing, dy is equal to 0. And here we'll have an initial condition as well, where we've seen before, the initial condition won't be considered until the very end. We'll solve this, and then at the end we'll plug this in. All right, so let's go ahead and confirm, make sure this in fact is homogeneous. Just because it's differential in form doesn't mean it's homogeneous. This could be an exact equation. We don't know off the top of our head. We don't know, so let's go ahead and check. Let's see. If I take this first one and I call it p of xy, I take this one, I call it q of xy, just for the sake of labeling things here. All right, so p of xy is equal to xy minus y squared. If I then take p of tx comma ty, this would be tx times ty minus ty squared, which is going to be t squared xy minus t squared y squared, which, since you have a common factor of t squared, that can be factored out, and we get t squared times xy minus y squared, which is in fact t squared times our original function. Okay, but that's not enough, right? This does confirm that p is homogeneous, in this case with degree 2, but we also have to confirm that q is homogeneous and also of degree 2. So here, q of x is negative x squared. So if I take q of tx comma ty, I'm going to get negative. The x gets replaced with a tx squared, which is going to be negative t squared x squared. And t squared can be factored out, writing that as t squared times negative x squared, which, you notice that's the same as q. We can write this as t squared times q of xy. So yes, they're both homogeneous, but just as importantly, they're both homogeneous of the same degree. So then this is a homogeneous equation of degree 2, which means we can solve using this technique. We're going to pick a substitution. It really is a free choice. Sometimes one is a little more complicated than the other, but that's not something you can know ahead of time. You just really kind of just pick one. So here we're going to substitute, and I'll just pick the first one. We'll say y is equal to ux. And either because you've memorized this or because you've derived it using the product rule, you're going to also substitute in that dy is equal to u dx plus x du. All right, so let's go and do that. Our problem looks like this. So anywhere I see a y, I'm going to replace it with ux. Okay, so that's going to be x times ux minus ux quantity squared dx plus a negative x squared times my dy is going to be replaced by u dx plus x du, and of course 0 just stays 0. Okay. So now let's go ahead and simplify this. Let's actually multiply things out and collect like terms. All right, let's see here. This is going to be ux squared minus u squared x squared dx plus, here we simply distribute, so this will be negative x squared u dx, negative x, I've been writing the u's in front, so let me continue that pattern, minus ux squared dx, and then minus a positive, so that'll be minus x to the third du is equal to 0. Here we notice that these both have a factor of dx, so really these should combine, this along with this. They both have a factor of dx. These are like terms. And in fact, I've got ux squared and minus ux squared dx. So really these just cancel out. Okay. So since those are both gone, really what we have is negative u squared x squared dx plus, and then here this one's gone, so I'm just left with minus x to the third du is equal to 0. Now one thing I note here is I have a common factor of x squared here and here, and technically here, right, because this is 1x squared, this is x times x squared, and this is 0 times x squared. So let me go and take advantage of that common factor. Technically, I'll just divide all the way across by x squared. Oh, and in fact, all these have negatives, right? So let me get rid of the negative by divided by negative x squared. All right, so the negatives are all gone. Here I'm just left with u squared dx. Minus a minus will be plus x du. And of course, this is still just 0. All right, so there we go. We've confirmed that it was homogeneous, degree 2. That was our first step. We completed our substitution here in our second step here. And then our third step has been to simplify, which we've done that. We've simplified down to this. And now we can reclassify. If you can already tell what this is, you might want to pause the video and see if you can solve that. If you have already solved that, let's go through it together. And if you haven't, well, let's go through it together anyway. This is separable. If it's not readily apparent that it's separable, it might be a little easier to see it if you go ahead and isolate one side. Let me take this to the other side over here. So I'm going to write this as x du is equal to minus u squared dx. Hopefully that's a little more obvious that it's separable. And if it's not, well then we divide this over this way, divide this over this way, and integrate. Here we have the integral. Let's see, I've got du over negative u squared is equal to the integral of dx over x. And yeah, clearly separable. So now integrating this, we end up with, well, that's just the natural log of x. Absolute value, yeah. And then over here, the integral of negative 1 over u squared du, that's just going to be negative 1 over u. Technically, these all have constants of integration, right? So let's go ahead and put those on there. Although we are going to combine them here in just a moment. Let me actually just do them separately at first. All right, so let's see. I'm trying to... Oh. No, you don't need a negative on here, because here if you use the power rule, that's a negative 2 power. So it'll be the negative of a negative. So my apologies. That's a negative, but then when I integrate, it becomes a positive. There we go. All right. All right, so now, so here we've solved, but this is still in terms of u, isn't it? Remember, we've done a substitution. U isn't actually a variable that we care about. In fact, it's not even a variable that we had in the first place. U was simply the substitution y over x. And you can divide the x over this way. So right here, when we say 1 over u equals c1, 1 over u plus c1 is equal to natural log of absolute value x plus c2. Really, this means we're taking the reciprocal of u, which means we're taking the reciprocal of y over x. That's x over y. So here we get x over y. Let me go ahead and subtract this to the other side over here. So this gives me natural log absolute value x. C2 minus C1, that's just another constant. I'll call it C3 like that. And now I can isolate I can solve for y here. Here I can, run out of space there a little bit, but here I can solve for y, I'm going to go ahead and reciprocate. If I take the reciprocal of this side, that's the same as taking the reciprocal of this side. As long as both sides are defined, you're okay with doing that. So this is y over x equals 1 over all of this stuff. And you can multiply the x to the other side. So you get y equals x over natural log of x plus c3. And there we go. But that's a general solution. Notice this is a one parameter family of solutions. We have an initial condition. This is an initial value problem. So we're almost done. But what we need to do now is we need to plug in if x is 1, y is 1, and then solve for our c here. All right, so here we go. So now our initial condition was if x equals 1, y equals 1. So let's plug that in and see what we get. We get, 1 equals 1 over natural log of 1 plus c3. Now the natural log of 1 is 0, so this is gone. So we get 1 over c3 equals 1. Oh, well then clearly c3 must equal to 1. Okay, so then our particular solution to the initial value problem is going to be y equals x over natural log absolute value x plus 1. Oh, actually, so I haven't exactly made a mistake in my algebra, but there is a little issue here. Notice that natural log of absolute value of x is continuous and defined for all real numbers, except 0. You can't take the natural log of 0. But if you remember, all solutions to a differential equation must be differentiable and therefore must be continuous. Okay, so I have to exclude 0. So if our solution, it's continuous and fine, and everything's good except at 0, well, okay, I have to disallow 0, but then I also have to choose one side or the other here. So here, without any other without any other information. No, we do have other information. We have that we have to include x equals to 1. All right, so here we cannot get rid of this part because this is where x equals positive numbers, including 1. So we'd have to get rid of this part. So here, although this is a perfectly valid solution in terms of the integration and the algebra and such, our final result actually has to be y equals x over natural log of x plus 1, like this. No absolute value. We don't care about this stuff back here. So we only want where everything's positive. So that would be on the interval from 0 to infinity. And there we go. That would be our final answer. Because remember, you're not allowed to include any discontinuities, but then if there's a discontinuity, then you either have to choose everything on one side of the discontinuity or everything on the other side. You have to have the largest continuous piece. Here we need the positive part, so we disallow the negative part. So that will be our result. Right, now, for our next type of problem, let's go ahead and have a definition here. Let's define what we mean by a Bernoulli equation. A differential equation of the form derivative of y with respect to x plus some function of x times y is equal to some function of x times y to the power n. This is called a Bernoulli equation. One thing to note, if n is equal to 0, well then anything to the power 0 is 1, right? So that's just going to go away right there. And that would be a linear equation, wouldn't it? It'd be y prime equals function of x times y plus function of x. That's linear. If n is equal to 1, well then that's pxy equals qxy. Those are just like terms. They're both something times y. You could just combine the like terms. So you would end up with derivative of y plus function times y equals 0, because you could combine the like terms and there'd be nothing left here, which would also be linear. So if n is equal to 0 or n is equal to 1, it is technically a Bernoulli equation, but really you just consider it a linear equation. So if n is 0 or 1, don't even bother with this. Note, if n equals 0 or n equals 1, then just think of that Bernoulli equation as being linear and solve that way. Don't even bother with this technique that we're about to talk about. Is it wrong to use this technique for something that's linear? No, not at all. It's just more work than is necessary. All right, so now let's go and take a look at the technique that would work for a general Bernoulli equation where n is 2 or higher. And again, it's a substitution. This technique is for solving Bernoulli equations dy dx plus px times y equals qx y to the power n. All right, so first of all, and I think I'll put it in the technique as well as in the note here, if n equals 0 or n equals 1, then solve as a linear equation, as an equation linear in y. And just be done with it there. However, if n is greater than or equal to 2, then we're going to multiply on both sides. Oh, I shouldn't even say greater than or equal to 2, because technically this n can be, it can be negative, right? So I shouldn't even say that. I should just say if n is not equal to 0 or not equal to 1. If n is not 0, if n is not 1, then you're going to go ahead and multiply on both sides. Multiply across by 1 minus n times y to the negative n. And then step number 3, you're going to then make the following substitution. Substitute u equals y to the 1 minus n and solve this now linear equation. Now, Bernoulli equations, if you perform these 2 steps, will become linear. If they start off linear, awesome. If not, they'll become linear. So let's consider an example of doing this. Let's consider y prime plus xy is equal to x over y to the power 3, where y is not equal to 0. This is not an initial condition or anything like that. It's just highlighting the fact that, yeah, this won't be 0, so you're fine. You can divide by it. Okay. All right. So here I'm going to rewrite this in a way that makes it fit the pattern from our last technique a little more directly. I'm going to write this as x times y to the minus 3rd. Okay. So here that clearly does fit the pattern here. This is the derivative of y plus some function of x, in this case it's just x, times y is equal to some function of x times y to a power. And that's why over here I said, oh, I shouldn't say n is greater than or equal to 2 because technically n can be negative. And in fact, let's go with an example where it is negative. All right, so here our n will be negative 3. Which means 1 minus n is going to be 1 minus a negative 3, 1 plus 3, that's 4. Like that. Thus, 1 minus n times y to the minus n, that's what our technique says we're multiplying by. We're going to multiply across by 1 minus n times y to the minus n. That's going to be 1 minus n was 4. And then we're going to take the negative of this n. Since it's already a negative, it'll become a positive. So you get 4y to the third power. So that's what we're going to do. We're going to now multiply all the way across by 4y to the third power. So 4y to the third power times y prime plus 4y to the third power times xy is equal to 4y to the third power times xy to the negative third power. All right. Here, these two cancel out. Y to the third and y to the negative third. Looks like that. And so here we get, well, let's see, not much else simplifies out. Here we get 4y to the third, y prime, plus 4x y to the fourth power. Let me write that as, just y to the fourth power like that. 4x to the fourth power. And then over here, I'm just left with 4x. Okay. Now, one thing to notice here, 4y to the third y prime. That's the derivative of y to the fourth. Remember, y to the fourth is a function. So when I take the derivative of y to the fourth, I get 4y to the third. But then because y is a function, I would have to multiply by the derivative of y because of the chain rule. So this right here is exactly the derivative with respect to x of y to the fourth. Like that. So now, once we have multiplied across by 1 minus n times y to the negative n, in other words, by 4y to the third, we're not going to use a substitution that anytime we see y to the 1 minus n, we're going to call that u. Well, 1 minus n was 4, which means that anytime we see y to the 4, we're going to just call that u. But we see that twice right there. So this is going to be the derivative with respect to x of y to the fourth is just going to be called u. 4x, y to the fourth, again, that's u, and that's equal to 4x. But that's linear. Notice that's a linear equation. Here, this is du dx plus, this is our p of x times u equals q of x. That's a linear equation. And because of that, we're now going to use an integrating factor. Our integrating factor is going to be e to the integral of p of x dx, which that's our p of x, it's 4x. So here that's going to be mu is equal to e to the integral 4x dx, which is what, that's 2x squared. So here that's going to be e to the 2x squared. Technically, there's supposed to be a constant of integration here, plus c, since I've integrated. But remember, for an integrating factor, we don't need a family of integrating factors. We just need a single one. And because of that, we're allowed to choose any constant we like. And here I chose my constant to be 0, plus 0. You can always just leave constants off for integrating factors. So now what we're going to do is we're going to go ahead and multiply across by our integrating factor here, our e to the 2x squared. And that's going to give us, let's see, that'll be e to the 2x squared times du dx plus, let's see, that'll be e to the 2x squared times 4xu is equal to e to the 2x squared times 4x. This multiplied by integrating factor all the way across. And now remember that the whole point of an integrating factor is to make the left-hand side be the result of having used the product rule. And notice right here that if I just say this is this left side, I can write this as the derivative with respect to x of the product of u with e to the 2x squared. Because sure enough, if you use the product rule here, that's going to be the derivative of the first one times the second plus the first one, that's your u, right there, there's your u, times the derivative of the second one. Here that would be just, the derivative of exponential is itself, but then take the derivative of the power because of the chain rule. So this entire expression here on the left side of the equal sign is just the product rule on u times the exponential. On the right hand side, nothing's happened yet. I'll just write it down, 4x e to the 2x squared, like that. And now I'll integrate on both sides. Okay, so now let's integrate across on both sides with respect to x, of course. Here, the integral with respect to x of the derivative with respect to x of this function is just this function. So here we get u times e to the 2x squared equals, and here the antiderivative is nice because notice that 4x dx is the derivative of this, so this is just e to the u du. So the entire thing is just e to the u. So this whole thing here is going to be e to the 2x squared. Of course, we do have a constant of integration, and technically for both, plus c1 plus c2, but since I know I'm going to combine them anyway, I think I'll just put it over here. I'll just call this plus c3. I went ahead and skipped c1 and c2 and just jumped directly to c3. Okay, so now let's see. So I'm trying to solve for u, which means I can just divide now on both sides by e to the 2x squared. So I get u is equal to, this divided by itself is just 1, but then I've got c3 divided by e to the 2x squared. I'm dividing by something that has this power, this positive power, so I think I'll write it as just a negative power up on top. I'll write this as u equals 1 plus c3 times e to the minus 2x squared. Having a negative power just brings it up to the top like that. Okay. But finally, keep in mind that u is not actually a variable that you started with. U is a substitution that we made up here at the beginning. Right here, let's see, u was a substitution for y to the 4th. So going back over here, we get that y to the 4th is equal to 1 plus c3 e to the minus 2x squared. Just like that. And let's see, this didn't have any initial conditions, right? No, it didn't. Okay, so this would be our result. Now for our last technique that we'll see here, let's go ahead and consider one more substitution, and this is reduction to separation of variables. There's one kind of equation which this specific type of equation reduces down to be separable. Reduction to separation of variables. For dy dx is equal to some function of a polynomial of x and y. So you have the derivative of your function is equal to a function of a polynomial, where specifically this one should not be 0. If this or this are ever 0, that's fine. and that they usually won't be, but if they are, that's okay. But this one definitely cannot be 0, because otherwise then you don't have a function in y, where b is not equal to 0. This one is very, very straightforward. It's a function of a polynomial. You just take the whole polynomial and substitute it for u. So we're going to substitute u equals ax, that's your first step, ax plus by plus c, the whole thing. And then once you've done that substitution, then you separate variables. This is probably the shortest one. Solve by separation of variables. All right, so let's, I hope I have enough room here for an example. Let's give it a try. So for example, let's say I have dy dx is equal to 1 plus e to the y minus x plus 5. So here you have a function of a polynomial. The polynomial is plugged into something else. You may have, sine of a polynomial or cosine or exponential or logarithm, but the polynomial as a whole is a term. Is a term in the problem. All right, so here we go. Let me do this off to the side to try to save a little space. Here, take the polynomial y minus x plus 5 and just call that u. U equal y minus x plus 5. Okay, well then that means that du is going to equal to, let's see. Well, it's just the derivative, but in differential form. So here that's just dy minus dx, and then the derivative differential of a constant is always 0. So this is just du is dy minus dx. It's just the derivative in differential form. So then that means that if I take du dx, so du dx is equal to dy dx minus dx dx, which is just 1. Thus, my dy dx I can isolate, and I get that dy dx is equal to du dx plus 1. Okay. So now I have my substitutions. This one is the one that's obvious. You're just told, hey, the polynomial, you're going to call that u. So this right here is our u. But what's not obvious, which that was what this was about, was finding what dy dx is going to be substituted by. So here I am going to now get, let's see, my dy dx is going to be du dx plus 1 is equal to 1 plus e to the u. 1 plus e to the u, like that. Well, I've got a plus 1 on both sides, so I can just subtract 1 and those cancel out. So really, this is just du dx is equal to e to the u. The ones just canceled out. And now I can integrate on both sides because this is now separable. I can go ahead and write this as, that'll be integral of, that'll be, if I divide this over to this side, that'll be e to the minus u du is equal to the integral of 1 dx. So that's nicely separable now. And now I can go ahead and integrate. Here, if I integrate e to the minus u, I get minus e to the minus u plus a constant. If I integrate 1 with respect to x, I get 1x plus a constant. And that should be a c plus c1 right there and a plus c2, which I'll just combine to give me a c3 like that. Okay. Let's see now. I guess I'm trying to isolate my u here so that I can take my negative and just divide across by a -1. So this would be e to the minus u is equal to now minus x, and then if I take this constant and divide by a negative, it becomes the negative of that constant. But you know what the negative of a constant is? It's another constant. So I'll call that one c4. So minus c4 like that. So now to get at my u, I can it's already exponentiated. I can take the logarithm on both sides. So that's minus u equals the natural log of negative x plus c4, like that. And then I can multiply both sides by a negative 1. So this will give me u is equal to negative the natural log of negative x plus c4. But keep in mind that u is not actually a variable that you cared about. U was this substitution. So now let's back substitute. So this gives me that y minus x plus 5 was negative the natural log of negative x plus c4. And finally, to get my y by itself, here I can explicitly solve. I could just add the x and subtract the 5 to the other side. So in the end, I get y is equal to x, that's now a positive, minus the natural log of negative x plus c4, and then minus 5. Okay. And that would be our solution. No initial conditions, right? Yeah, and that would be our solution using this technique. So that is it for this section on substitutions. Note that we don't actually have new techniques. We have ways, instead we have ways of using a substitution to reduce our problems down to, so that we can use older techniques. That's it for the problem, and that's it for this section. If you have any questions, please let me know, and I hope you all have a nice day.